Hi there, welcome back to this channel. In this video, we're going to be talking about the refraction of light through a triangular prism. Now, you must have seen this formula before that says that sine, that a refractive index of glass is equal to the sine of half of refracting angle plus minimum deviation over half of A. All right. Now, what we are going to be doing is we are going to be establishing this relationship, this formula, essentially. Now, you see, in a triangular prism, we've said before that a prism is a substance that has the capacity to separate light into the distinct, the different wavelengths that are present in a polychromatic light. Now, for a certain polychromatic light, when it is incident on a prism, when it is incident on a glass prism, it is going to be split into different fractions. And how does this happen? It happens by the phenomenon known as refraction, So, and that is because of the optical density of a prism. Now, a prism is a substance, an optical element that has polished flat sides that at least two of the side has an angle, and this angle is known as the refracting angle. And this refracting angle has a lot to do about the refraction, the angle of refraction of that substance. Of course, the nature of the glass also has a lot to do because it depends on that. It determines the refractive index, the refraction of the light, the level of refraction of the light that would occur in that glass. So what I'm saying in essence is that when light travels through prism, as it comes from a vacuum or from space into the speed at which it travels diminishes because of the optical density of the glass through which it travels. Now the following are very important to note. Now, first, we know that the refractive angle of the prism determines the refraction of the light also. So there are different dimensions of triangular prisms. There are triangular prisms that have the triangles that use equilateral triangles throughout, so that the triangles are 60 by 60, 60, 60. That is, the three sides, the three angles are equal, and there are some that use 90, 45, 45. Is that okay? So that is the difference. Now this is an isosceles triangle, the one that uses this, and the one that uses this is the equilateral triangle. So those are the two different types of prisms that we have. Well, our focus today is going to be on the equilateral triangle because that is where we can get this equation as it is here. All right, the first thing you should remember is the equation of refractive index. So refractive index is equal to sine I over sine R. Okay. Now, having known this, we know that when a ray of light, so let me draw this guy to be bigger. So we know already that when a ray of light is incident on this guy, on this surface, so we call this the incident ray. Now, we draw it with respect to the normal. Bear in mind that normal is always drawn with respect to the interface. It is directly perpendicular to the interface, the surface of that prism. So it should be drawn at right angles to the flat surface of that prism. Now, when light is incident on here, the incident ray, remember, it is read from the normal to the angle of incidence, to that side, not from the plane. Is that okay? It is read from the normal to the angle of incidence. And you see, so this ray is supposed to continue this way, this direction. Now, when this guy enters into the glass, it's going to be deviated. So, and that deviation is what is known as refraction. And this refraction here, the first refraction that happens here, we name it R1. Bear in mind, because it enters into this prism, it's going to travel at a different speed from that of when it was in space here. So by the time it enters here, the speed changes, and because of that, the light is deviated in its direction. So bear in mind also that this line represents the actual path it was taken beforehand. And by the time it gets here on the other side of the prism, it also, we call it the emergent ray. It also goes in this direction, and we call this the emergent ray. This is also read with respect to the normal to the surface. So this will be the emergent ray. So you will notice that it started in this direction and went in this direction. So it is deviated. And this place from here to here is called our deviation. The angle, the difference between here, where the final path of the light ray and the initial path is going to be the deviation. And there are two deviations that we always take note of here. This is the maximum deviation or total deviation. This is called the total deviation. All right. But there are smaller deviations that we can take note of here. So you're going to notice that this guy is coming from here, right? So it means that this is also a refraction. This is also a refraction here, R2. Because if we looked at it as though the light ray were entering from here, it means it has refracted in this direction also. Do you understand that? So this is R2. And then the difference between here and here is also our deviation. So the angle of refraction, the angle of refraction, R1 will be here. Excuse me, R1 will be here. Do you know why? I said it is read from the normal to that line. So we read our angle of incidence is read from normal to this line of incidence. And also, this is our line of refraction. It bends, right? The angle of the line of deviation. So as it deviates here, we also read it with respect to the normal that was drawn there. So the first refraction happened here. Do you understand that? All right, so here also the second refraction happened here. Seeing that this ray might have, we could consider it as, say that it came from here, and this would be our emergent ray there. So because it's coming out here, we call it the ray that emerges. So the emergent ray. And this is going to be our angle of emergence because it must be read with respect to the normal to that surface. All right, so this is going to be our first deviation. And then also you will see that now from here, it has also gone in this direction. So if we were to read it in this direction, we're going to have another deviation D2. We're going to have another deviation. Because if you follow the path of where this is coming from, and what that means is that as it entered here, it deviated here. So as it's going out here, it means it's also deviated from this line. So this is going to be deviation 2. Just follow along with me. So if we look at this, we will say that deviation 1 is going to be D1, and that would be the angle of incidence minus the first refractive angle of refraction. All right, and this is going to be the first deviation. Then the second deviation is going to be the emergent ray minus the second refraction, the second angle of refraction, and this is going to be the deviation, the second deviation. So that the total deviation or total deviation that is going to be the addition of the first deviation and the second deviation, and that becomes I minus R1 and E minus R2. All right. So after now that we've known this, we know therefore that the deviation from the normal path is given by this formula. Now, the next thing to take note of is the fact that this is the angle of refraction, and it's 60 by 60 by 60, so it's an equilateral triangle. Now, the minimum deviation occurs. The least deviation that can ever occur here occurs when the minimum deviation, we affectionately denote it by D mean. Is that okay? So the minimum deviation that occurs here occurs when the angle of incidence is equal to the angle of emergence, and therefore because of that, the R1, the refraction that will take place, the angle of refraction, the first angle of refraction, and the second angle of refraction will be equal. So you see, minimum deviation occurs when what? Because it is an equilateral triangle. So you expect that as the ray of light is incident here, So under an ideal case, as the rate of incidence, the angle of incidence should be equal to the angle of emergence. So I is equal to E, and that is when minimum deviation occurs with this triangular prism. And also, R1 is equal to R2 in this point, because of course I is equal to E, therefore the refractions that should be experienced within the same prism should be equal. So if this is the case, therefore, what you will notice is that since R is equal to R2, I is equal to E, therefore what we basically have here in this equation is I minus R in both cases. So we have 2I minus R. Do we understand that? 2I minus R. So I mean R because both angle of refractions are now equal. All right, so that is why we have this. But also bear in mind that, so I said that minimum deviation occurs when it is equal to this. Bear in mind also that for an equilateral triangle, exclusive of an equilateral triangle now, that is for a prism with equilateral triangles, for an equilateral triangle, at minimum deviation, at this minimum deviation, the angle of refraction is also equal to half of the refracting angle A. So for an equilateral triangle, at minimum deviation that is expected, the angle of refraction is half of that refracting angle, the refracting angle, and it could be anywhere, it could be here, depending on how the angle, the prism is turned. All right. So if this is the case, and we already have this, then we can begin to manipulate. So we could call this, let's call this our equation 1. So total deviation, D is this, equation 1. This would be equation 2 at minimum deviation. This is equation 3. Okay, so we could manipulate and substitute equation 1 into equation 3 into 1, so that we have 2, so that D minimum would therefore be equal to 2 into brackets I minus R is now 1 over 2A. Okay, what this means is that if we want to make I the subject of the formula, what we'll do is that D would have D min over 2 is equal to I minus A over 2. That is, you understand that? So what now happens is this guy comes here, we have I is equal to D min. This guy comes here, becomes plus A all over 2. Okay, so this is equation 4 already. All right, then recall from our first equation. Okay, this will be our first equation there. Okay, let's make it equation 5. This is our fifth equation. We already know that the sine of angle of incidence is equal to over sine of angle refraction from Snell's law is the constant for any given pair of media. So what we have is that we can now substitute or into equation 5, substitute equation 4 into equation 5, so that we have sine of D min plus A all over 2 over sine of R is A over 2. And that is how the formula is derived. All right, so that will be it for this video. In the next video, do well to subscribe to the channel so that you don't miss out any of the other videos that are coming. I'm going to do many things on light waves, and I'm going to simplify the topic for you so well that you will understand it perfectly. God bless you, and subscribe to the channel and click the bell notification to get notified whenever I drop a new video. Thank you.